presence of either an intense magnetic field or a binary companion influencing the star's evolution. If a secondary star is present, its gravitational interaction could be sculpting the expanding gas, directing it along preferred axes. This would explain the sharp edges seen in the nebula and the apparent lack of chaotic turbulence that typically characterizes similar objects. The central star is likely in an advanced evolutionary stage, either approaching a transition to a Wolf-Rayet phase or nearing its final collapse. The material ejected into space could be part of a larger process in which layers of stellar atmosphere are shed over time, nebulae that persist long after the original outburst. The exact mechanism behind the symmetry remains a topic of ongoing study, hypotheses ranging from episodic eruptions caused by internal instability to a controlled expansion influenced by a strong toroidal magnetic field. Spectroscopic analysis reveals that the nebula is rich in both silicate and carbon-based dust, suggesting complex chemical interactions occurring within its expanding shell. Ionized hydrogen and oxygen lines indicates exposure to intense ultraviolet radiation, which is slowly altering the composition of the surrounding medium. These processes are crucial in enriching the interstellar environment with heavy elements that later contribute to the formation of new generations of stars and planetary systems. The velocity of the expanding gas of the nebula has been evolving for thousands, though it is unclear whether it has remained stable over time or if it has undergone significant changes in structure. Some researchers propose that the formation is an optical illusion, where a more cylindrical or bipolar outflow appears squared due to our viewing angle. Others argue that external influences, such as a dense interstellar medium or remnant stellar winds, may be reinforcing the straining material along specific planes. Advanced telescopes equipped with high-resolution spectrographs are expected to provide more precise data on the velocity distribution of gas and dust. By analyzing how light interacts with different regions, astronomers hope to reconstruct the three-dimensional shape and determine whether the observed symmetry is an inherent property or a temporary phase. If the central star is approaching a supernova event, its surrounding nebula could dramatically brighten as the explosion interacts with the ejected material, similar to what has been observed in other massive star systems. Comparisons to other structured nebulae suggest that mass loss in massive stars follows patterns that are more organized than previously thought. While planetary nebulae often display symmetric forms due to the expansion of shells around dying stars, this particular exhibits a level of precision that challenges conventional models. If magnetic forces are indeed playing a dominant role, it may suggest that similar structures could exist elsewhere but remain undetected due to their orientation or distance from Earth. Infrared observations have also hinted at the presence of complex organic molecules within the nebula, which could have formed through photochemical reactions triggered by high-energy radiation. Such environments are thought to be crucial in the early stages of planetary system development, as they contribute to prebiotic compounds that later become part of interstellar dust clouds. Understanding how these materials evolve in different stellar environments provides insight into the chemical diversity of the galaxy. Future research will focus on mapping the precise movement of gas within the nebula and determining whether external factors are influencing its evolution. If a binary companion is confirmed, it could provide further evidence that multiple star systems are a key factor in shaping structured nebulae. Long-term monitoring may reveal subtle shifts in brightness or morphology, indicating ongoing dynamic processes that have yet to be fully understood. If the central star eventually undergoes a supernova, it could transform the surrounding region by sending shock waves through the nebula, triggering secondary reactions and possibly altering its structure. The resulting supernova remnant would provide valuable data on how pre-existing mass loss affects the aftermath of stellar explosions. If a neutron star or black hole forms at the core, it may interact with the surrounding material in ways that produce additional high-energy emissions, making it a potential source of radio waves or X-ray bursts. The precision of the formation continues to challenge existing astrophysical models, suggesting that either previously unknown mechanisms are at work or that magnetic shaping plays a far greater role in stellar evolution than currently. Upcoming telescopes with adaptive optics and interferometry will provide deeper insights into the processes governing the expansion of ionized gas and the interaction between radiation and dust within the nebula. While its ultimate fate remains uncertain, its significance as an astrophysical case study is undeniable. Whether it is a short-lived phase of stellar evolution or a long-standing feature that will persist for thousands of years, it represents a rare and valuable opportunity to study the forces that shape the most massive stars in the cosmos. The answers it holds could refine our understanding of how stars evolve, how they lose mass, and how they influence the galactic environment over cosmic timescales. The forces responsible for shaping this nebula remain a subject of debate, with multiple mechanisms potentially working in tandem to maintain its strikingly structured form. The presence of a dense circumstellar medium suggests that earlier events may have interacted with surrounding material, creating shock fronts that reinforce the observed geometry. If stellar winds or episodic eruptions from the central star were directed by an unseen companion, their effects could have compounded over time, gradually sculpting the nebula into its current configuration. Magnetic fields are another possible factor influencing its development. In some high-energy astrophysical environments, magnetic pressure can guide ionized gas along preferred paths, constraining outflows, jets, or symmetric globes. If this phenomenon is occurring here, it could help explain the sharp definition of the nebula's edges and the near-identical structure on opposite sides of the central star. Observations of other massive stellar remnants have shown that even weak magnetic fields can have a profound impact on outflow dynamics, reinforcing the nebula's shape may be magnetically driven. The chemical complexity of the surrounding another layer of intrigue. The discovery of molecular hydrogen and polycyclic aromatic hydrocarbons within the nebula suggests that the region has undergone prolonged exposure to ultraviolet radiation, leading to chemical reactions that produce complex organic compounds. If this material later becomes part of interstellar clouds, it could contribute to the formation of planets or even prebiotic chemistry in systems. This highlights the role of evolved stars as sources of heavy elements but also as potential contributors to the early chemistry of planetary environments. The velocity distribution of ejected material is also a critical factor in understanding the formation. If the gas is expanding uniformly, it would suggest that the star has been losing mass gradually over an extended period. However, if velocity gradients are detected, with some regions moving faster than others, it could indicate a source of energy, possibly linked to a hidden binary companion or internal stellar instability. High-resolution spectroscopic studies will help determine whether the structure has remained stable or if it is actively evolving, with changes in morphology providing additional clues. Comparisons to other known stellar outflows provide valuable context for interpreting this structure. The similarity to bipolar planetary nebulae, which are often shaped by binary interactions, suggests that the nebula may represent an earlier stage of this process in a much more massive system. If future observations confirm the presence of an orbiting companion, it could provide strong evidence that binarity is a key factor in the formation of highly structured nebulae, challenging existing models of single-star mass loss. The possibility of a central star in a terminal supernova phase adds an additional layer of urgency to ongoing research. If this is a pre-supernova system, then the surrounding nebula may play a crucial role in determining the characteristics of the eventual explosion. A dense circumstellar medium could shape the supernova's light curve, producing an extended afterglow or even influencing the type of remnant that forms. If the core collapse results in a neutron star or a black hole, interaction between the compact object and the surrounding nebula's secondary emissions, including high-energy X-ray or radio bursts. Some researchers propose that this nebula represents a previously unrecognized category of structured stellar outflows, distinct from both planetary nebulae and classical supernova remnants. If so, it could mean that highly organized mass loss occurs in more stars than currently expected but remains undetected in systems with less favorable viewing angles. Advanced three-dimensional modeling, combined with data from next-generation telescopes, will be necessary to determine whether similar formations exist elsewhere in the galaxy. Long-term monitoring will be essential to track any changes in the nebula's structure. If subtle shifts in brightness or gas distribution are detected, it could indicate ongoing mass loss or dynamic interactions within the expanding material. Alternatively, if the nebula remains unchanged over decades of observation, it would suggest that its formation was driven by a past event rather than processes occurring in the present. Either scenario will provide valuable insights into how massive stars shed their outer layers and how those layers evolve over time. The nebula's role in the broader astrophysical landscape extends beyond its immediate surroundings. If it is indeed an example of a structured pre-supernova outflow, it could help refine predictions for other massive stars nearing the end of their life cycles. Understanding the processes shaping this formation could improve models of how supernovae interact with their environments, potentially leading to better interpretations of historical supernova remnants observed throughout the galaxy. Future research will focus on uncovering the underlying drivers of the nebula's symmetry, whether they be magnetic forces, binary interactions, or stellar dynamics. Upcoming missions and observational campaigns will provide increasingly detailed data to answer fundamental questions about the role of evolving shaping the structure of the interstellar medium. Regardless of what mechanisms are ultimately responsible, the nebula remains a rare and invaluable opportunity to study the interplay between stellar evolution, mass loss, and the physical forces that govern the cosmos. As observational techniques continue to improve, new details about this enigmatic formation will likely emerge, shedding light on the precise mechanisms responsible for its near-perfect symmetry. The role of radiation pressure in shaping the expanding gas is an area of active investigation. Stellar winds could be driving material outward along well-defined paths. If the star is emitting energy anisotropically, with stronger radiation in specific directions, it could be influencing the way ejected material disperses into space. This could help explain the structured nature of the nebula, particularly if interactions with a surrounding dust disk or magnetic field are reinforcing its geometric appearance. High-energy phenomena may also be contributing to the evolution of this structure. Some researchers suggest that the presence of shock fronts, regions where fast-moving gas collides with slower material, could be shaping the expanding nebula. These interactions create areas of increased density and ionization, altering how light scatters and giving the nebula its distribution. If these shocks are being driven by periodic stellar outbursts, then the formation could be the result of multiple ejections over time, each adding to the overall complexity of its structure. Infrared observations continue to provide new insights into the dust and gas composition of the surrounding environment. Data suggests that the dust grains within the nebula are relatively large compared to those found in diffuse interstellar clouds, possibly indicating that they have undergone significant processing due to radiation collisions. If this region is rich in carbon-based compounds, it could support the idea that evolved stars contribute not only to heavy element enrichment but also to the formation of molecular precursors essential for planetary system development. Determining the age of the nebula is another critical aspect of research. By analyzing the expansion velocity of different gas layers, astronomers aim to estimate when the initial mass ejection occurred. If the nebula is relatively young, it could be the result of a recent instability in it, whereas an older formation would suggest a more gradual mass loss extended period. This distinction is important in understanding whether this structure is a transient phase that will evolve into a more diffuse remnant or if it represents a long-lived phenomenon sustained energy input. The potential presence of a binary companion remains a crucial question, as its confirmation would provide a strong explanation for the nebula's nature. If a secondary star is orbiting the central object, its gravitational influence material into specific flow patterns, producing the observed. Some models suggest that if a white dwarf, neutron star, or even a black hole is present, accretion-driven out spontaneous striking shape. Identify variation the primary star indirect signs of a hidden X-ray or radio emissions may help resolve this mystery. Further study of the polarization of light from the nebula will be useful in determining whether magnetic forces are playing a significant role in its evolution. If light scattering patterns indicate the presence of aligned dust grains, it could suggest that a strong magnetic field is guiding the expansion of gas. Such a scenario would align with models of magnetically collimated, which have been observed in other astrophysical environments, including young stellar objects like galactic nuclei. One of the most abilities is that this formation represents a stage of a process that has not been widely documented in astrophysics. If it turns out to be a precursor to a more well-known structure, such as a planetary nebula or a supernova remnant, it could provide a unique opportunity to study how these phenomena develop over time. Observing changes in the coming years will be crucial in determining its future trajectory, whether it will eventually dissipate into the interstellar medium or continue evolving complex structure. If the central star ultimately undergoes a supernova, the surrounding material could play in shaping the explosion's observable characteristics. The presence of dense circumstellar causes significant interaction between the supernova shockwave and the pre-existing nebula, leading to an unusually bright and prolonged event. If this occurs, it could offer direct observational evidence of influences the final stages of massive star evolution. Long-term monitoring with next-generation telescopes will be essential in answering the remaining question of this extraordinary structure. Instruments capable of resolving fine detail distribution, magnetic field orientation, and spectral properties will provide the data needed to construct a more complete picture of its origins and evolution. If similar objects are identified elsewhere in the galaxy, it may indicate that these types of structures are more common than currently believed, potentially leading to a re-evaluation of existing models of stellar mass loss. Regardless of its ultimate fate, this nebula remains one of the most visually striking and scientifically valuable examples of how complex forces interact in the late stages of stellar evolution. Whether shaped by binary dynamics, magnetic fields, episodic outbursts, or a combination of multiple factors, its existence challenges physical theories and offers an unparalleled opportunity to study the intricate processes governing massive stars. Future observations will undoubtedly bring new discoveries, deepening our understanding of how these cosmic structures form, persist, and eventually transform into the next generation of celestial phenomena. As observations continue to refine of this extraordinary formation, the interplay between multiple astrophysical forces becomes increasingly apparent. A perfect symmetry that a finely tuned combination of stellar winds, radiation pressure, dynamics, and possibly magnetic confinement is at work. Each of them contributes to shaping the expanding shell of gas, maintaining its structural integrity over time. Whether this lesson is an inherent certain types of stellar outflows or a rare coincidence of conditions remains an open question. Infrared spectroscopy has revealed variations in the temperature and density within the nebula, that it is not a uniform shell, complex, layered structure. This suggests ejection events may have occurred at different times, each adding a new component to the overall formation. If past eruptions have been episodic, by internal instability star or with an orbiting companion, could be an progenitor's mass loss history. The specific ionized elements in the surrounding gas, high-energy radiation from the central star is actively chemical Regions exposed to the most intense ultraviolet and X-ray flux exhibit signs of ionization-driven radiation, while more shielded areas retain heavier molecules and dust grains. This dynamic environment provides insights into how stars influence their surroundings, the interstellar medium within their interiors. Primary challenges in understanding the nature of this, determining whether its symmetry is a transient or a long-term result of a recent outburst. It may slowly degrade over time as the expanding material interacts with it. On the other hand, if it is stabilized by ongoing processes, mass flow or a persistent magnetic field, its geometry may remain largely unchanged for thousands of years. Tracking subtle shifts in the nebula's brightness and morphology over successive observational periods will be essential in distinguishing between these possibilities. Comparisons to other known examples of structures that ordered mass ejections are more common than previously assumed. However, the degree of symmetry observed here is exceptional, indicating that specific conditions must be met for such formations to arise. Surveys identify objects in different regions of the galaxy could provide a broader statistical foundation for understanding how often these structures occur and what factors contribute to their development. Numerical simulations model the potential scenarios for this system. By incorporating variables such as stellar rotation, pulsation-driven mass loss, and binary interactions, researchers hope to replicate structure and determine which forces evolution. Results suggest of rotation and a companion's gravitation could create flow patterns of the nebula's distinct shape. If these moderate, they could offer a new perspective on the role of binarity in shaping circumstellar environments. Another intriguing aspect is the potential for future variability in the central star itself. If it is nearing the end of its evolutionary cycle, further may lead to ejections or luminosity fluctuations. Such changes could provide direct observational evidence of how the inflowing stellar brightening event occurs. It could be a sign of an impending transformation, possibly signaling the transition into a Wolf-Rayet phase or even the terminal. Ultimately, unlap supernova, the surrounding nebula could play a role in shaping the aftermath. A dense pre-existing medium and an unusually energetic explosion, with shockwaves producing intricate interaction patterns within the already structured outflows. Such would be a rare opportunity to observe how massive stars influence their own supernova environments, offering insights into the processes that stages of stellar. Long-term monitoring efforts will focus on changes in expansion velocity levels and thermal emissions within the nebula. Any deviations from the expected indicate nodes at work, potentially revealing new stellar outflows. With upcoming space-based observatories providing increasingly detailed data, a clearer picture of this remarkable phenomenon continues to emerge. Whether this structure is an exceptional part of a broader, yet underappreciated category of organized mass ejections, its study is reshaping perspectives on how stars interact with their surroundings. Versus maintaining its near-perfect symmetry remain one of the most compelling mysteries in modern astrophysics, and future discoveries may provide the missing pieces needed to unlock its true nature. Regardless of what new revelations come to light, it stands as a striking test of and often unexpected beauty of such a structured formation raises fundamental questions about the longevity of and the mechanisms that sustain their geometry over time. If the observed symmetry is not merely a transient effect, ongoing processes maintaining its precise form. One possibility is that the radiation pressure from the central star is continually shaping the expanding gas, reinforcing existing structures and preventing dissipation. In this case, Variations in stellar lead to subtle but measurable shifts in the nebula's morphology, offering insights into how radiation-driven mass loss influences environments. The presence of complex molecular compounds within the expanding shell suggests that chemical evolution is occurring on a large scale. As ultraviolet and X-ray radiation interacts with dust and gas, it triggers photodissociation processes that break apart existing molecules and encourage new ones. This cycle of destruction and recombination is key to understanding how massive stars contribute to the molecular diversity of space. If the conditions with the existence of increasingly complex, further enriching the surrounding medium. Velocity mapping of the nebula's another avenue that may yield crucial insights into its formation history. If different layers are expanding at distinct rates, it could suggest multiple episodes of mass ejection, each contributing to the overall structure. By reconstructing the motion of individual gas clouds within the nebula, astronomers can determine whether the expansion is accelerating, slowing down, or maintaining a steady rate. A uniform velocity distribution would support the idea of a single, well-coordinated outflow event, while irregularities could indicate ongoing dynamic interactions between different layers of material. The role of external influences, such as interaction in interstellar medium, is also worth exploring. If the expanding nebula is encountering regions of higher density gas, it could be experiencing external pressure that helps define its shape. This scenario is particularly intriguing because it would imply that the large-scale structure of the medium plays an active role in shaping stellar remnants. If such interactions are confirmed, they could offer a broader understanding how similar nebulae form across different galactic environments. Advances in computational astrophysics are enabling the development of increasingly sophisticated simulations that attempt to recreate the conditions necessary for such a structured formation. Incorporate factors such as rotation, magnetic fields, radiation binary gravitational effects. Determine whether a single dominant force is responsible for shaping or if multiple factors are working together in a complex interplay. Early results suggest that while radiation magnetic fields produce organisms of a binary companion, significant likelihood of long-term symmetry. If a compact object is a system, it could further complicate the dynamics of the nebula. A neutron star or black hole companion the surrounding material through accretion-driven winds or relatives. These high-energy processes create additional nebula, potential regions of enhanced or density variations observed in different wavelengths. If variations detect X-ray emissions or rapid fluctuations in radio signals, a direct evidence remnant playing an active role in the system. Another aspect of whether this nebula represents evolutionary shares characteristics with other known structures at different stages of development. If similar formations exist noticed due to unfavorable view, it could such ordered massage common than prismatic survey nebulae using high resolutions could help identify additional, refining our understanding of the conditions necessary for their formation. Future of the nebula, as its fate will lie in the evolution of its central star. If the star continues shedding mass, the surrounding structure may gradually expand thousands of years, blending into the interstellar medium. Alternatively, if the star undergoes a more dramatic transition, such as collapsing into a white dwarf or black hole, it could leave behind it that continues to interact with the surrounding. If this leads to periodic bursts of energy, the nebula may experience episodic reillumination, creating a variable emission profile that persists long after the initial mass ejection event. If a supernova does occur within the nebula, it is the most visually and scientifically interesting remnants ever observed. The pre-existing structure would shape the way the supernova shock wave propagates, creating patterns of glowing filaments and ionized gas. The resulting explosion could provide valuable data on how mass loss before core collapse affects the properties of the supernova itself, offering a real-world test case for theoretical models of stellar death. Regardless of its this nebula remains an astrophysical anomaly that continues to challenge conventional understanding. Its striking symmetry, dynamic environment, and potential connection to high-energy astrophysical processes make it an ideal subject for continued study. The combination of observational data, theory, and future technological advancements promises to unlock further insights into the mechanisms responsible for shaping such extraordinary cosmic structure. In the broader context of stellar evolution, this nebula highlights the diversity of pathways stars can take as they approach the end of us. Whether it represents a transient phenomenon or a more persistent stage of mass loss, it serves as a reminder that the processes governing the formation and evolution of stellar remnants are more intricate than previously assumed. As research continues, each new discovery will bring us closer to understanding the fundamental forces that sculpt the universe's most fascinating and mysterious celestial object. As more data is gathered, the intricate dynamics of outflow become clearer, yet many aspects remain elusive. The balance between stellar wind pressure, radiation forces, and gravitational interactions is delicate, and minor fluctuations in any of these variables could signal the nebula's morphology over time. If its current shape is maintained for an extent, it would suggest an ongoing regulating mechanism, possibly a consistent mass loss cycles and external constraints imposed by either a magnetic field or a binary companion. A deeper understanding of motion of the gas is static. If gas and dust are flowing outward at a uniform velocity, then the expanding out significant turbulence. Within the outflow exhibit differentiation that multiple processes simultaneously. The presence of streams could point to localized shock wave material remnants of mass. If the star at the center is rotating rapidly, it could also be affecting the pattern. Fast rotation alters the shape of the stellar atmosphere, making it an enhancing equatorial mass loss through centrifugal forces. This would naturally produce an extended disk or toroidal structure around the star, for the broader nebula. If rotation is a key factor, then future spectroscopic studies of the star's surface may reveal Doppler broadening effects, indicating differential velocity regions across its surface. The role of ionization fronts within the nebula is another aspect of interest. If the central star's radiation is continuously exciting the surrounding gas, it may be forming stratified layers where different elements are ionized at varying depths. This would lead to a multi-tiered composition where hydrogen, helium, oxygen, and heavier elements are distributed according to their ionization potentials. Understanding these ionization boundaries could provide insight into how far the star's influence extends and whether the outer regions of the nebula are still actively shaped by radiation or are merely residual structures from the possible presence of molecular clouds within that complex between gas phase solid particles are occurring. Dust plays an important role in astrophysics, acting as molecule formation by providing surfaces where atoms can take place more efficiently. If the nebula is carbonaceous or silicate dust, it may indicate that material from the star is condensing into solid form, eventually contributing to the raw material for future planetary system formation. One key observational goal is to determine whether the nebula is optically thick or if it allows significant amounts of radiation to escape. If it is largely transparent at certain wavelengths, then light from the central star may be escaping in directed beams, influencing surrounding interstellar clouds beyond the immediate boundaries of. This could result in faint emission regions detectable in infrared or radio wavelengths, providing clues about how the nebula interacts with the broader galactic environment. The possibility of a faint, extended halo surrounding the main structure is also being explored. Some nebulae exhibit diffuse outer layers, where lower density transitions into the surrounding medium. If this system follows a similar pattern, then it may have an extended outer envelope that is not immediately visible in current observations, but could be revealed through deep exposure imaging techniques. If such a halo is present, it may contain older material from earlier mass ejections, offering a more complete picture of the star's long-term evolution. Further study of light polarization within the nebula may also help in determining whether magnetic fields are contributing to it. If dust grains are aligned along a preferred axis, it could indicate that an underlying magnetic field is shaping the flow of ionized gas. Strong magnetic confinement could explain why material appears to be expanding in a highly organized manner rather than dissipating irregularly, as is typical in many other stellar outflows. High-resolution radio observations provide additional evidence of magnetic influence by detecting synchrotron radiation, which occurs when charged particles spiral along magnetic field lines. The long-term monitoring of the nebula's brightness and shape will provide important clues about its future evolution. If no significant changes are observed over the coming decades, it could suggest that the system has reached a stable equilibrium, where within it counterbalance one another. However, if gradual shifts in emission intensity or structural features are detected, it may indicate that the nebula is still undergoing active reshaping, driven either by continued mass loss or external forces acting on the expanding shell. If the central star eventually transitions into a degenerate remnant white dwarf or neutron star, its interactions with the nebula may take on new characteristics. A cooling white dwarf would emit lower energy, potentially altering the structure of the nebula over time. If a neutron star or black hole forms, accretion of remaining material could generate episodic bursts of high-energy emissions, indicating the evolution of the surrounding gas. With the advent of more sensitive instruments, including future space-based and ground-based telescopes, finer details of the nebula's composition and kinematics will become accessible. Multi-wavelength combined infrared and X-ray researchers to construct an increasingly of the processes governing this remarkable. By extending coverage to different electromagnetic spectra, physical interactions may be revealed, providing additional pieces to the puzzle of its formation and persistence. Understanding this nebula has broader impact beyond its immediate structure. If similar objects are discovered in different star-forming regions or other evolved stellar systems, it could indicate that such formations represent a recurring phase in the life cycles of massive stars. This would provide new constraints on theories of stellar mass loss and the role of binarity, magnetic fields, and radiation pressure in shaping astrophysical outflows. It would bring us closer to universal principles that govern the transformation of stars and the lasting impact they leave on their environments. Research continues. The nebula remains a fascinating subject at the intersection of multiple astrophysical disciplines. Its structured appearance challenges traditional models, suggesting that either previously unrecognized mechanisms are at work or that known processes are operating in a more complex manner than currently understood. Gain from this system will not only refine our mass loss in evolved stars but may also influence broader concepts in astrophysics, from supernova progenitors to the formation of chemically enriched regions within galaxies. No matter what observations reveal, this nebula stands as a striking testament to the intricate and often unexpected interactions of the cosmos. The persistence of such an intricate and symmetrical structure suggests that it is not merely a fleeting phase but a system governed by sustained forces. If the nebula were purely the result of an explosive event, its features would have begun to dissipate in a more chaotic fashion over time. Instead, the defined edges and organized outflows indicate that ongoing mechanisms are reinforcing its structure, preventing it from dissolving into an irregular cloud. Understanding the stabilizing forces will provide crucial insights into how long such formations can persist and what role they play in the broader galactic ecosystem. One of the key aspects of and dust within the nebula are interacting with interstellar magnetic fields via the influence of the central star. If so, the entire system may be embedded within a larger-scale magnetized region that is influencing This would mean that its shape is not solely the result of internal stellar processes so being conditioned by environmental factors on a much larger scale. The interaction of expanding nebulae with the magnetic field is a relatively unexplored area of research, but it could have profound implications for understanding the formation of structured outflows in other astrophysical settings. The possibility that part of a larger feedback loop within its local stellar neighborhood avenue of study. Mass loss from the central star is feeding circular clouds. It could be triggering secondary star formation in nearby regions. In this scenario, the nebula, byproduct of stellar evolution but an active participant in the recycling of matter, enriching the interstellar medium and influencing the next generation of star formation. If observations detect enhanced star-forming activity in adjacent regions, support the idea that evolved stars contribute more direct chemical evolution than previously. Infrared imaging continues to reveal variations in dust grain size and composition, suggesting that material within an undergoing active processing. Some regions appear to contain larger, more carbonaceous compounds, possibly formed through prolonged exposure to violet radiation. If dust grains within the nebula have been altered by repeated ionization cycles, they may exhibit unique spectral signatures that could serve as a marker for similar objects elsewhere in the galaxy. By identifying the specific types of molecules present, users may be able to determine whether it is conducive to the formation of organic precursor systems. The thermal structure of the nebula is another critical factor in assessing its long-term stability. If the gas within it is being heated unevenly, localized instability, leading to subtle structural time. Temperature maps created from multi-wavelength observations could reveal whether certain regions are cooling more rapidly than others, potentially setting the stage for condensation of material. If dense clumps are forming within the nebula, they could eventually collapse under their own gravity, leading to the formation of new stellar objects. While this would be an unexpected outcome of this type, it cannot yet be ruled out. The search for very brightness of the central star remains ongoing. If the star exhibits periodic fluctuations in luminosity, it may indicate pulsational instabilities affecting its outer layers. These variations could, in turn, influence the mass loss rate, leading to episodic enhancements in the nebula's structure. If brightness changes are detected, correlating them with observed changes in the nebula's emission patterns could help establish a direct link between stellar activity and the evolution of the surrounding material. The outermost layers of the nebula are of particular interest, as they may provide a record of its earliest formation stages. If weak shock waves are detected propagating through the outer edges, it could suggest that the nebula is still expanding into previously undisturbed interstellar space. These shocks could be producing low-density filament to detect an object but may be revealed through radio observations. If such features are confirmed, they would provide valuable clues about the nebula's expansion dynamics and whether it is still actively interacting with its environment. One of the most significant remaining uncertainties is whether this structure represents a phase that other massive stars undergo or if it is an exceptional case. If similar objects exist but have not yet been identified, it could mean that such nebulae are more common than previously thought but remain undetected due to observational limitations. Searches using next-generation enhanced sensitivity red and radio bands whether this is part of a broader class of stellar outflows that have gone largely unrecognized. If the nebula is closer to a supernova event, its surrounding structure may serve as a unique observational target when the explosion occurs. The interacternova shockwave and the pre-existing circumstellar material could predict patterns of emission, allowing astronomers to witness the complex interplay of and nebular evolution. The ability to study such provide unprecedented into how influences the properties of supernova explosion, helping to refine models of core collapse dynamics. The continuing refinement of models incorporating data from this nebula, better understanding of the high-mass stellar environment. As computational capabilities advance, simulations will be able to incorporate increasingly detailed physical parameters, allowing researchers to test different formation scenarios and compare to observational explanation for the nebula's. It will not only most intriguing astrophysical mysteries but also framework for understanding similar objects that may be discovered in the future. Regardless of what new findings emerge, this nebula remains a compelling example of the complexity of stellar evolution and the diversity of rise from seemingly chaotic. Its continued study will provide valuable insights into how stars interact, how mass is redistributed, and how the final state of evolution shaped the interstellar medium. Each new observation to uncover behind formation, revealing the intricate and often unexpected ways in which stars leave their mark on the cosmos. As research progresses, the long-term evolution of this nebula remains compelling. Structure will remain stable for thousands of years or graduate into the surrounding interstellar medium is still unclear. If the forces maintaining its symmetry weaken over time, the well-defined edges may begin to blur as expanding gas. However, If there are persistent shaping mechanisms such as ongoing stellar mass loss, magnetic field interactions, or external pressure from surrounding interstellar clouds, the structure may remain largely intact for an extended period. Observations in multiple wavelengths continue to refine our understanding of the nebula's internal structure. Radio observations, for instance, are useful in detecting cold gas may not be visible or infrared light. If significant amounts of molecular gas are present, it could indicate that the outer layers of the nebula are cooling and condensing streams or localized high-density regions. These structures, if conjecta and the surround. The distribution of heavier elements within the nebula if enriched nitrogen and carbon are concentrated in specific regions, it could suggest of gates or are influencing chemical processes. Detailed spectral analysis reveal an earlier nuclear fusion central star or if they are the result of more recent nucleosynthesis in an stellar. Another nebula is determining whether it is interacting with external gas flows from other nearby stellar sources. If the region around contains additional matter influencing the expansion structure, this would suggest symmetry is not solely properties are lack. Such interactions, they could insights into how massive stars shape their surroundings on a larger scale. The question of whether the central truly alone responsibility binary companion to precise measurements and high-resolution imaging. If a compact such as a neutron star or white dwarf orbiting within the system, its gravitational effects could be contributing to the organized shape of the surrounding area mass ejection events, which would be consistent with the layered appearance of some regions within the nebula. Essential galactic fields is another factor under examination. If the nebula's shape is influenced by interactions suggest that it is not an isolated phenomenon but part of a broader network of interconnected astrophysical processes. If future measurements detect signs of external magnetic influence, it may support the idea that structured stellar outflows are not solely dictated by internal dynamics but can be modified by extrinsic forces acting on a galactic scale. If this nebula does eventually undergo a transformation due to a supernova explosion, the resulting remnant could provide a rare opportunity of how a pressured outflow interacts with a high-energy shock. Such an event would likely produce an asymmetric supernova remnant, with expanding material encounters in some directions while escaping more freely in others. This would create a high emission pattern, providing valuable data on how circumstellar matter influences the outcome of core collapse events. Even if a supernova does not occur in the near future, the nebula's gradual evolution provides important insights into how mass loss continues in late systems. Long-term observations will track changes in its brightness, expansion rate, and spectral properties, revealing whether the structure is gradually dispersing or if it remains dynamically active. If the nebula continues to exhibit stability over time, challenge existing theories of mass ejection